So now we're just going to look at one example, just one example. So what this says is that we have an inductor, right, that is connected to a supply of 250 volts. To 250 volts, 50 hertz. So that's a supply that we are connected. So this is basically the RMS, this is basically the frequency, right? And an inductor takes a current of 5 amperes, right? The coil dissipates this, right? So mean that because what is here means what true power, right? So we are trying to calculate the resistance and the inductance, right? And we know the symbol for this: resistance will be CB, R, inductance will be L, right? Okay. So now we have all the data we need, and the power factor is just the PF, which we've seen to be the cos theta, or the cos whatever angle, right? Okay. Now let's do this. What are we trying to find? This whenever you have a question, you know the data you have, write the equations down and look for, it makes your work easier, and look for the what you need, right? So resistance, right? So now that we have resistance, what do you think we have to use? Let's see. So if we have resistance, right, we could do V on I. But then again, the circuit here, yeah, we won't just resistance. So the circuit here, you know that this AC, right? So V on I. Do we have the voltage? Yes, we have the voltage. Do we have the current? No. Right. But how do we do that? Let's see. The whole circuit here is having both. So that will mean that we won't be using just V is equal to IRL. No, we want to analyze the whole circuit, right? What we use V is equal to what IZ, right, to analyze the whole circuit, because you have an inductor, you have inductance, and you have some sort of resistance. Right? So that will mean that we have to find this resistance first. This resistance. So we have to find this impedance, right? And then that will help us to find the current, and we'll be able to find the resistance. One other thing that could make your work easier is that you draw the circuit, right? You draw a circuit diagram just to represent what you're doing. So we have an inductor, right, connected to a supply. So let's see, sinusoidal. So we have an inductor here connected to supply sinusoidal, right? So it should be right. Okay, yeah, and we are seeing that this one is 250 volts and this is 50. Let's try this out. 250 volts, and then it's what, 50 hertz, right? And then the core, well, it's having a resistance, so meaning that because it's a material, I have some kind of internal resistance, right? Let's see. So let's put something small here. Let's say it's part of it, because we said the inductor will have, it's still a wire, but though it's coiled, it still have internal resistance. So let's see. Let's just draw this side out. So like this. To this side, yeah. So it has some internal resistance. So we have R, right, which is a small r, internal resistance, and then you have the L, which is the inductance, right? Yeah. So we've simplified it. It takes a current of 5 amperes, right? And the cord is speeds at 750 watts. They're just the resistance side. Let's see. This resistance here gives 750 watts. Because of that small internal resistance, that's how the small r that we have. Okay. All right. So now we are trying to find Z first, right? That helps us to find I, and then we move on to find what's it? We move on to find both the resistance and the inductance, right? So this is how we go about it. So let's see. Okay. All right. So have we been given the current? Okay, I think we've been given the current already. Okay. So we need, first of all, we need resistance and then inductance, right? So let's see. So, and then the current across, even that this one is given, the current is given already, so we don't need the current. So that means that the equation that we'll be using, so basically that means that we need R, and then we need what, L, right? And then this R and L, let's see. We have to find one of them, right? Or we can find the other. But then we need Z, right? Okay, so let's see. So the voltage, so basically the equation will be equal to V is equal to what? IZ. We know the voltage. Let's see. What is it? We know the voltage across the inductor, the coil, and we know the current across it. So we can find the Z. That means that Z is equal to V on I. You don't always have to go through this, but when you get the understanding and then you have a problem before you, you know what part you must use to get the what do you call it? So to get the what do you call the problem solved, right? So we are going to do that. Just follow the basic, as in the fundamental, right? The basic understanding, and apply that, and then I think we'll be able to solve any question that you have, right? So let's see. So the voltage is what? 250, right? So let's see. Okay, 250. And then the current is what? 5, right? So what do we have? 50 amperes. Sorry, 50 ohms. 50 ohms. The unit very important. So 50 ohms for this, right? And let's see. So we found the impedance, right? So now we need the resistance and the inductance, right? So let's see. So because we have power there, and we know that what's the name? When we see resistance, it's the only thing that's related to power, active power, true power, right? So and then we have that power here already. So we have that power here already. So meaning we can do something to that to find the R, right? So let's see. We have power, so to I squared R. So that will mean that this is internal resistance. So just write small r. So that will mean that this area we're looking for will be P on I squared, right? And then we know the power is 750, right? And then the current is what? 5. 750 on 5. That gives us internal resistance in the core of 150 ohms. Wait, this should be squared. So it's not 150. Okay. So power is 750, current is 5, squared of that gives us what? 30 ohms, right? So now we have the resistance. The next thing for us to find will be the what's the name? The inductance, right? But then we know that the inductor is related to two equations, right? We have let's see, we have reactance, right? XL we go to 2 pi frequency and this, and then we have another one where we have L, right? And then we have di dt, and then we have v, right? Vt, right? Yeah, so that's it. But then because we're not given the time function of the voltage or the current, we are not going to use this. But at some point we use that. But this is the one you're going to use, right? Okay. But then we need this. We have this, we need this. And then we can find this directly. This we can get from Z, which we've already found. And we know Z is equal to, Z squared is equal to R squared, right? In this case, because it's internal resistance, write a small R squared, right? And then we have plus, and then we have X squared, and then we have R squared plus, you can skip the side if you know the questions already, but I just want to see what we've done so far. We have XL minus XC, or the squared, right? This Z squared. And what do we need? We need XL to find our L, right? So this is what we do. That will mean that, but in this case, you don't have capacitor, so that means there's no capacitive reactance, right? So this goes out. So if you are trying to find XL, that will mean that we'll have a XL will be Z squared minus R squared, and then we take a square root of that, right? And that will give us our XL. Okay, so let's see. We have our Z to be 50. So 50 squared, and then our R was internal resistance, small r, 30. Let's see what we have for that. Third, when I'm punching this, I have a way I punch it just to make my work easier. So if I skip something, the calculator will just see error to let me know that I'm missing something. 50, 30. Okay. So I end up getting an XL of 40. 40 watt ohms. Very important, the unit. So as a result, that will mean that to get L, right, that will mean I have a XL on 2 pi f. We have all these values already. So that's 40 on 2 pi times what? The frequency was 50. 50, right? So yeah. So have 40 2 pi times 50. Right. And this is what it gives me. The inductance I have. And remember that the unit for inductance, that's what? Henry. So basically I have 0.127, let's do 40p 3 Henry. Right? If you want, you can change the unit to make it something simpler. So we have, let's see, can do milli. Can do milli. So that will be times 10 to the power 3. I'm introducing the milli, right? So we must take it out with the 10 to the power 3. So that will mean that this 10 to the power minus 3, right? So that will mean I have 1.273 millihenry, right? So a minute. I'm missing something. If I'm multiplying by this, a milli is 10 to the power minus 3, right? So 10 to the power 3. Yeah. So that's what I missed. 10 to the power 3. That will give me, you can just do it this way, you don't need the calculator. So 1, 2, 3. Right. So that'll give me 127.3 millihenry. Right. So that's what I have. So now we've solved the first part, reactance, resistance, and inductance, right, of the core. Now we need power factor, right? We know power factor. Remember that it basically has to know the portion of the apparent power that's true, not that's active, right? So let's see. So B. So we have B, and we have cos this, right? And that's basically a P on S, right? Do we have apparent power? No. Do we have the true power? Yes, right? But then, because we do not have the apparent power, this is what we do. We said we have power, but we don't have apparent power. But we know that one is just IV. So that's it, the RMS value, which we've already been given. So let's see. And then we know power is what? 750. Right? That's true power, active power, or just power. 750. And then I is 5. Right? And then B, we're given like 250. Let's confirm. Yeah, 250. There's a 250. Okay, 250. Okay, so we have 750. We have 5 times 250, and that gives us 0.6. A power factor of 0.6. But then there's one thing about the lagging and the leading. So we'll talk about that very fast. So let's see. But then let me see. Can you have a guess? Have a guess whether it's leading or lagging, the power factor leading or lagging. Okay. So basically it will be what? Lagging. Why? Let's see. So we said that when it comes to, when I talk about the elements, the RLC, we have a resistor, we have inductor, and we have a capacitor. Right? And then basically the current to be here and the voltage will be the rest, right? So if we have just purely, if you have a combination, it depends whether that combination, whether it's lagging or leading, right? Here's the case. What are we having in the circuit? We have a resistor and we have an inductor, right? Meaning that the resultant, right? The resultant, what's the name? Apparent power will be here because we have what? An inductor, that's a coil, and a resistor. So meaning the apparent power will be here, right? But if we're to have a resistor and a capacitor, the would have been here, but that's not what we have. In this case, we're having what? A resistor, a coil, or inductor, which basically has an internal resistance. So the apparent or the resultant power will be here. The apparent power will appear here, right? So that will mean that what's happening, who is leading, meaning that what's the name? The current is lagging the voltage. And when it comes to power, the one that we use is as a reference is of what do you call it? The current, right? We use the current to see whether the current is leading or lagging the voltage. And in this case, because the apparent power is here, this is current, this is for voltage, right? The current is lagging the voltage, right? So as a result, we see that because the current is lagging, then the power factor 2 is lagging. Right? So power factor lagging here, right? Right. Let's go over this one more time. But then because resistor is here, we know that what will be here. We know that power will be here, right? And then apparent power will be here. Reactive power is here, right? But why? We are comparing what this power factor here, which is this, is comparing what power or true power and an apparent power, right? And because we are comparing them, let's see, this one is leading. Power is here, apparent power is here, and then we know that when we are doing this related to the Cartesian coordinate system, this is plus x minus x, this is plus y minus y, right? And we read in what direction? On the positive x-axis, so read this one. That means that current is behind what? The voltage. So as a result, because current is lagging voltage, and then we have what we call power lagging the apparent power, then we see that the power factor is what? Lagging. So 0.6 lagging. So that's how come we have that. So 0.6 lagging. It's lagging. All right.